So in this method, we're going to talk a little bit about Euler's method for systems of differential equations. And this is good for you to understand. I'm not going to require you to do these by hand, but it's good to kind of know how, because a lot of the on the internet or software that draws the phase portraits and stuff like that for you are using Euler's method. So it's good to kind of know how it works. And it is actually very similar to the Euler's method for just a single differential equation. So shouldn't be too bad. So let's start out with some notation. So if we have dx, if we have a differential equation, dx dt is equal to some function involving x and y, and then we have dy dt also involving some other function of x and y, then we can write that, of course, in vector notation. And this is stuff that I think we've all talked about before, but just to remind you. And that would look like this. dy dt is equal to, oops, that's a capital Y. That's how we kind of make the distinction between, when we talk about capital Y, we're talking about the vector that involves both the x and y. And that's going to be equal to capital F of capital Y. And of course, capital Y is x comma y. Is some function, is the coordinates x and y. Okay? And capital dy dt is equal to a vector valued function like this. Okay? So that means that capital F of y is going to be equal to f of x comma y. That's this guy up here. And the y coordinate will be g of y. G of x, y, I guess I should say. Okay, so that's a little notation. So f is a vector valued function. Okay. And you can use a vector value function to produce the vector field. Like those vector fields are, we've drawn mostly directional fields, but the directional fields come from the vector fields. We just make all their vectors the same length, so it becomes a directional field. And we can, this function, of course, is what we'd use to produce that vector field. And a solution, of course, would be a curve on that vector field whose tangents are vector, whose tangent vectors at any point agree with the vector field. So a solution, if we have a vector field that's going like this, you know, maybe it goes like that somewhere else. A solution, if we draw a solution, that means that at any point, if we stop and check, the tangent vector at that point should agree with the vector field. And that one didn't really there. So anyway, that's what we mean by a solution in regards to the vector field. Okay? So really, we could say that f of x comma, f of x comma y is a velocity vector. Because if we're following this path and at any point we stop and say, well, that is my f of x comma y, and that is my f of x comma y, and that, you know, because they're just vectors. So that would be a velocity vector. If we have a particle that's moving along this path, that would be the velocity of that particle. Okay. So for Euler's method, what we're going to do is basically use these velocity vectors to calculate the next point. So let's say we start at the initial point of x initial x and initial y, right? And so basically what we're going to do is we're going to use these initial points and the velocity vector, excuse me, to get a new point. So that means that in general, x sub 1 comma y sub 1 would be equal to x sub 0 comma y sub 0 plus some little change in t, just like we did before in the Euler's method, times f, capital F, evaluated at x naught and y naught. So if you think of it this way, we've got this initial vector. So we're starting at the point x naught, y naught. We got this initial vector that is my f evaluated at x naught, y naught. And we're going to multiply it by some little fraction. So change t. So we're not going to go all the way off this vector. It's going to be somewhere, say, right about there. And then that would be my new point. That would be my x sub 1, y sub 1. And of course, you do the same thing with x sub 2. So x sub 2, y sub 2 is going to be equal to x sub 1 comma y sub 1 plus the change in t times f evaluated at x sub 1 comma y sub 1. Of course, we keep doing that. So that's the notation. But the way it works out actually is if we have my dx dt is equal to small f x comma y, and my dy dt is equal to small g x comma y, and we have an initial value of x naught, y naught, and we have a step size of change in t, which is some small number, then we're going to say that there is a slope essentially. So we're kind of trying to connect it to what we did before. And we'll have another slope n. That would be g of x sub k, y sub k. So then we get this equation. If we want to know what the k plus 1 term of, or the k plus 1 x coordinate, that's going to be equal to the k sub, or x sub k. This should be k, x sub k plus 1. That would be equal to x sub k plus small little change in t times m sub k. And y sub k plus 1 would be equal to y sub k plus some little change in t times n sub k. So basically it's the same as the singular Euler's method applied to one different equations, just applied twice with two different equations. So let's do a quick example. Okay, so let's say that dx dt is equal to y, and dy dt is equal to negative 2x minus 3y. And my initial value is 1 comma 1, and my step size is going to be 0.25. And we're going to do, we'll just do a couple steps here. Okay, so if I want to know what the first term is, or so that this is my x, my initial x and y. So my first x is going to be equal to 1 plus 0.25, because that's the step size, times my derivative evaluated at this point. Well, there's only one value to plug in, just the y, so I plug in 1 there. And I get that x sub 1 is equal to 1.25. Do the same thing with y. Y sub 1 is going to be equal to 1 plus 0.25 times, and now I'm going to plug 1 in for x and 1 in for y, because that's my initial value. So that would be negative 2 minus 3, which would be negative 5. So negative 5 times 0.25, that'd be negative 1.25. So it'd just be negative 0.25. So my initial point was 1, 1. And then my next point was 1.25. 1.25 comma negative 0.25. Let's do one more iteration of this. So then if I want to know what x of 2 is, that's going to be 1.25, because that was my x coordinate of the x of 1. So that'd be x of 1, yeah. Plus 0.25 times the dx dt evaluated at this point. Of course, I only have a place to plug in y, so I plug in a negative 0.25 there. And that is going to be 1.1875. So 1.1875 would be my x-coordinate. And then my y sub 2, that's going to be equal to negative 0.25 plus 0.25 times, and now we've got to plug my negative 0.25 into this equation. So negative 0.25 times negative 2, that would be positive 0.5 minus negative 3 times negative 0.25. Oh, whoops, I plugged the wrong thing. Take that back. Negative 2 times 1.25 is what I should have done. That would be negative 2.5. And let's see, if I negative 2.5 times 3, that would be positive 0.75. If we add those two together, we get negative 1.75. So put a negative 1.75 in there. And what do we get? Let's see. Negative 0.25 minus 0.25 times 1.75. And I get roughly negative 0.6875. And that would be my y coordinate, negative 0.6875. So it went from 1, 1 to 1.5, 1.25 to negative 2.5, and then it went to 1.1875, comma, negative 0.6875. And you can see if we just keep doing this, it'll just keep producing new coordinates. And we can draw, so each one of these points would be connected by a line segment, and that would be an estimate of the curve. And you can see if we make the step size really small, we could draw a curve that's pretty close to the actual solution. All right.